Thank you very much for coming to my talk. The topic that I would like to speak about today is something that I started to work on with Valerio. It's the multistability and transitions in the Earth system on longer climatic scales or shorter weather scales. And I'm particularly interested in the situation where in an intransitive system, the Basin boundary is not a simple geometrical object, but a fractal. In an intransitive system, we have coexisting attractors, which have their own basin of attraction, and there is this boundary between them, which is what I mean is a complex object. So I start my talk with flashing up a few motivating examples, multistability in geo or astrophysics. One of these is the snowball, snow-free bistability of the Earth. We worked together with Valerio on this, and I believe the next talk is about this problem mostly. And I will show how Kramer's theory is applicable to this problem when we consider the noisy situation when transitions are possible. So we have some exit rates from one state to the other, and we also want to describe the stationary probability distribution in this problem. Then I move on to the high-dimensional case, and I will be interested in here the transition paths across the Basin boundary from one potential well, as it turns out, to another one. So we have here a key object, the quasi-potential, that governs not only the exit rates, probability distributions, but also the transition paths. And then in the second part of the talk, I will talk about this specific situation of fractal Basin boundary. Even more specifically, it's a kind of rough fractal, which is something that we encountered with Valerio, working on the snowball snow-free bistability in a complex climate model. But then we discovered that this object has been known for quite some time. So I guess this slide doesn't need a title. This is Jupiter, a gas giant, and what is the matter of interest here is this zonal jet configuration. At different latitudes, you have many zonal jets, and they travel either in one direction or the opposite. The speed, the jet speed, has been even measured by space missions. First Voyager in 1979, then Cassini in 2000, and then latest in 2015. So we can see the latitude-wise velocity profile of these jets, and also see that over the decades there has been some variability, and this raises the question whether this is just a steady stationary vacillation of the system, or is it possible that we have some dramatic transitions from one configuration to the other. Now, this problem can be studied in barotropic quasi-geostrophic models on the beta plane. The classic paper by Charney and DeVore found two possible states in such a model. You can see the thick black lines as the contours of the stream function, so basically the winds. That in one case we have a wavy but fairly zonal flow, and in the other case we have this more meandering flow. It's called the block state. Of course, already in the time of this paper, this phenomenon had been known from meteorology. But in this particular model, this bistability seems to emerge as a result of orographic forcing. Those circles by the thin black lines show the contours of hills. I'm not sure it works well. But it looks like that orography is not needed. In another model by Farrell and Yonao, the authors also found a bistability of two single jet configurations, and in this case, the bistability seems to arise from some sort of symmetry of the system. Then, in yet another but similar model, due to Constantino, the authors found two coexisting jet configurations differing by the different number of jets. And the question arises that are these states transitive, or are they coexisting intransitive states? And some simulation result, but Eric Simonet did indeed find transition between these 2 and 3 jet configurations. I'm not saying that there is a transition with, between all sorts of configurations, but it's possible. Another example is the active and inactive summers in the Lorentz T4 model. Now, this is an extremely stripped down model of the global atmospheric circulation. Basically, it's a balance between the kinetic energy of the jet speeds given by x squared and some meridional heat transport facilitated by cyclonic eddies. And they are represented by y and z modes of the eddies. And we have some forcing of the system, thermal imbalance F, and we can introduce some seasonality in this. It was already Lorentz's original observation that the winters outside on the two sides of the dashed lines, the system is always chaotic, this system. And in the summers, it's more regular, but sometimes the summer is more or less variable. I didn't actually check out if it conforms to meteorological data, but let's just speak about this model as an example. If we fix the thermal gradient at an eternal summer configuration, then indeed we can find a coexisting periodic orbit as the middle one. And beside that, coexisting is a period 4 cycle. And we can even map out the Basin boundaries in a slice of the phase space. So the blue regions all go to the periodic cycle, the weak or inactive summer, and the white regions all go to the 4 cycle. Well, in this picture in the middle especially, the fractality of the Basin boundary is even more clear. Although this Basin boundary is not everywhere fractal, I believe it's a sporadically fractal boundary. But the chaotic saddle that is embedded in this Basin boundary, the red object, seems to be indeed a fractal object, a chaotic one, and I also drew in the unstable manifold of the saddle in green. It's quite similar to the winter chaotic attractor, actually. And due to the fractality of this Basin boundary, it can trap trajectories. So if the parameter shifts slowly, the parameter f, throughout the seasons, actually all the time, this chaotic attractor, snapshot attractor, is chaotic. For some parameter values, it's true that the 4 cycle or the periodic orbit is quite pronounced, but still trajectories populate a large part of space, phase space all the time. And finally, the third example is the snowball snow-free bistability. Now this is a quite dramatic feature of the Earth climate. And it can be, surprisingly, perhaps, modeled with the most simple climate model there is, a zero-dimensional energy balance model, which is just equating the tendency of the internal heat, internal energy of the Earth with the radiative imbalance, incoming and outgoing. The incoming is modulated by the albedo alpha, and the outgoing is just simply modeled here by a Boltzmann law, thermal radiation into space. And you can simply express the temperature from this equation to get the climatology. But it's not as simple as this, because the albedo is actually also temperature dependent. It's the reflectivity of the Earth. So if the planet is white, it's snowy or has a snow cap at least, it does increase the global albedo. On the other hand, if all snow is melted, the albedo is much lower, so the Earth can absorb more heat. So we have these two regimes reflected in the incoming radiation. For cold temperatures, high albedo, and low temperatures, high temperatures, low albedo, and there is some intermediate value between these. And depending on the solar strength, let's say, you can shift up and down this sigmoid, and then depending on that, you either have only a cold attractor, or only a warm, very warm, or you can have three solutions with a snowball and more moderate warm climate like ours today. So arguably, our Earth is actually not that far from this tipping point, from a warm to cold tipping point. And also, the temperature is not just a constant, there is variability in the climate system. It's customary to fit the global temperature by an AR1 time model, so it can be viewed as a stochastically forced system. So it makes sense to examine the question of stationary probabilities in this system, or exit rates from the warm climate. And these are the things that has been answered long ago by Kramer. His most important contribution within this theory is the famous Kramer formula for the exit rate. So the exit rate R can be defined in terms of an exponentially decaying probability that you find a particle in this potential well. And such an exponential decay would come from a simple linear ordinary differential equation. So from this you can just express R being minus the change of the probability over the probability, and this change of the probability P dot can be identified as a probability current, which can be expressed from such a conservation law of probability. And one can easily match this conservation law with the Fokker-Planck equation and express the probability current as the right-hand side of the Fokker-Planck. Now, we can introduce a function phi of x here, and with this we can describe the probability current in this form, just involving phi and the probability density itself. But phi does appear also in the probability density, because we can show that the stationary probability distribution is in this exponential form with phi as a power exponent. And this exponential form is coming just from the Fokker-Planck equation being a linear differential equation for d2 times w. And if you consider a constant diffusivity, which will suffice for us now, then we can identify this function phi by just the potential function fx, which is the integral of the drift coefficient d1. So the drift coefficient is appearing in the stochastic differential equation. It's just the right-hand side of the ODE, the unperturbed ODE. So we can integrate this equation for the probability current with respect to x from, say, the bottom of the potential well to some a across the barrier, and also observe that when the noise is very, very weak, the distribution is actually stationary, quasi-stationary, and from the conservation for the probability, it turns out that the S probability current is independent of X. We can also observe that the probability distribution at A is 0, so it cancels out. So we have this final formula for S on one hand, and we still need the formula for the probability, which is nothing but just integrating the probability distribution W in the potential well. And in this integral, we can express the potential distribution anchored to this minimum, the potential minimum. And with that, we have these cancelling terms in S and P, because for the exit rate, we are just dividing them. And the last step is that we observed that, in these two integrals, in one, the main contribution is coming from around x spin, and in the other integral, because of the sign change, here the main contribution is coming from the crest of this potential barrier. So we can expand these integrals, or the potential function, around these 2 points in quadratic form, which leads to exponential integrals here. And the solution of exponential integrals is square root of what have you, this constant in front of x squared. And this constant turns out to be the prefactor for the famous Kramer's exit rate formula. And otherwise, from these constants, from the expansion, we have in the exponent the potential difference. So the exit rate is determined by the potential function, by the potential difference, and the flatness of the potential crest and the bottom of the well. And this is unchanged also in higher dimensions. But there are two complications in higher dimensions. One is that the exit paths are non-trivial in this case. So in 1D that we looked at so far, there's only one way to go, through the crest of the potential well. That remains to be the case here, but how you get to that crest or saddle, that's not trivial. And the other complication is that in n dimension, the system might not be a so-called gradient system. The vector field might not be given by the gradient of a scalar function. Nevertheless, one can still look for the stationary distribution in the form of, in this exponential form again, with phi and z a prefactor. And if I don't show the details, if you expand the Fokker-Planck equation into a power series in terms of d, the diffusivity, then the leading order terms lead to an equation for phi, and the next leading order terms lead to an equation to the prefactor z. And the equation for phi turns out to be in the form of a so-called Hamilton-Jacobi equation. So you can use all tools in statistical mechanics the Hamiltonian takes this form in the Hamilton-Jacobi equation. And this way, it turns out that in the system going from one point to another, the path that you go through, most probably, is minimizing this, is minimizing the action, and that action is actually this function phi, a potential-like quantity. It's the action is an integral of a Lagrangian, and that's what we have. So we can actually write yet another ordinary differential equation for the potential, which can be solved alongside the Hamiltonian system of equations that come from the Hamilton-Jacobi for the path, the most probable path. So it's actually not easy to glean from here that the minimum action corresponds to maximum probability. But yeah, that's the case. And we can also note that this auxiliary variable P in this extended Hamiltonian system is a noise-like quantity because the first equation looks just like the original one, where P takes the role of noise. So that means that the system, considering also the second equation, has a trivial solution of P equals 0. And that means that the invariant objects of the original system are invariant objects also of the Hamiltonian, such as the attractor in the potential well and the saddle in the saddle point of the potential. And that also means that if we consider transitions, obviously the transition path has to go through the Basin boundary. And considering that it takes no action to move on the saddle, then as soon as you move out of the saddle, but within the Basin boundary somewhere, it immediately takes some action. So it's not going to be the most probable path to go to. Now, it's the most trivial thing that one wants to do in a system like this is to map out this potential function to see actually the potential wells and the saddle. But it's actually not so it's not practical to integrate these instanton equations and integrate along with the equation for the potential function, because you can only ever integrate with an initial condition. And the instanton is a one-dimensional object, but the unstable manifold of the attractor from which you want to start the integration is not one-dimensional. So it will take in the end some sort of minimization to find the instanton going this way. So there are other algorithms developed by Linear Schwartz and Tang et al., which somehow directly looks for the minimum of this action. I played around a little bit with this Hamiltonian instanton equations. So this is the situation in 1D. These trajectories winding around, these are the instantons. So if you want to go from the potential well up to the saddle point, the instanton would follow this path. But if you don't initialize the system exactly here on this path, then you just wind around, or your trajectory initialized on this other side would just diverge. So it's not a really good method, but this article by Barry does provide initial conditions which put you at least into the unstable manifold of the attractor, but that's only good in 1D. In 2D, immediately you have a 2D unstable manifold, and you won't hit the instanton with that initial condition. So you need to parameterize the initial condition and then do a minimization procedure. The discrete time formula, so in ND, in higher dimension, there is one more complication, which is the possibility of a fractal Basin boundary or fractal saddle within this Basin boundary. And as I said, because P equals 0 is a trivial solution of the system. Yes?
Just to understand, what do you call instanton precisely?
The most probable path between 2 points. So it doesn't necessarily, so it's mostly people mean paths from the attractor to one point of the attractor if it's chaotic, to one point of the chaotic saddle or saddle. But I believe any paths, any other paths can be called instantons which satisfy this maximum probability.
There's a particular solution of the Hamilton-Jacobian equations. Yeah, I know, but it's just a question of terminology.
So there is this complication that the phi is flat on the chaotic saddle. So phi does not select the most probable exit path. But instead, one needs to look at the complete probability distribution. And so it will be the prefactor in this probability distribution that will pick the most probable exit path. And you can get, as I said, an equation for the prefactor 2 from the Fokker-Planck. And then from the Hamilton-Jacobi, you can get yet another equation for the Hessian of the potential, this double derivative which appears in the equation for the prefactor. But as I said, don't integrate the Hamilton system and alongside with these. First, you need to find the saddle if you are interested in the potential difference only. Then you can determine the instanton by some direct minimization of the action or potential. And then you can use these equations to calculate the prefactor and select the maximum probability, most probable exit path. And fortunately, it's no problem to determine the saddle in a bistable system first, even if it's a very high dimensional one. This is what we did with Valerio, and the next talk will be about this. Then we can calculate the exit rate in n dimension as well, and still we find that the potential difference will play the key role. And this time, this prefactor has the Hessian, a double derivative, again of the potential function, but this time it's in n dimensional space. And if the system is non-gradient, there is an additional term appearing in the prefactor, and that's due to Freddy Boucher and Rainer. All this has been done also in discrete time for mappings, which can give a bit better insight in the problem, but I think I won't have time for this. I just want to point to this equation in the bottom, how you can calculate the potential, the action. So basically, in terms of the equation of motion, F is giving you the mapping, the discrete time mapping. You can define a cost function, and this is something that you can minimize. So basically, numerically, let's say you have a 2D phase space, you can just put a regular grid on the phase space, identifying grid points, and connect all grid points by all other grid points. So by this you have edges of a graph, and each graph is associated with this cost. And then you can apply an algorithm, let's say Dijkstra's shortest path algorithm, that finds you at the shortest path and thereby the potential. I managed to do this in the Hano map in 2D. So we have this two-cycle attractor in the bottom, and then trajectories escape that way. This horseshoe is the unstable manifold. But it's not an effective algorithm, unfortunately. Those by Tang et al. And Ira Schwarz are the go-to algorithm for this kind of problem. And finally, or in the second part of the talk, I would like to mention or speak about this specific type of fractal Basin boundary, which we came across in a high-dimensional climate model with Valerio between the snow-free snowball bistability. I thought myself that this Basin boundary is not going to be fractal, because the ocean system, which our ocean and ice system, is something that Michael Gill devised around the energy balance model, is not chaotic. It's a diffusive model. So I thought it's not going to be a fractal, but Arkady Pikolsky pressed this question, and Valerio suggested that we look into this. And it turns out that it's a fractal, and there is a known theory for that, or at least a theory in 2D. So there is a condition when you can have a fractal, when you perturb a bistable system. So in our case, it's the atmosphere perturb the bistable system, which features the snowball snow-free bistability and via the ice albedo feedback. So you need a more stable dynamics within the Basin boundary than across the Basin boundary. You need a larger Lyapunov exponent in the boundary than across. And this is the condition that was given by Grabosiot and York long ago. And a bit more recently, 10, 15 years ago, Jürgen Vollmer and co-workers derived again elegantly this formula. So basically, that's what I put up here. So X and Y are cross and in-boundary variables, and we are looking at the evolution of small perturbation of these variables, but such that the trajectory stays and the perturbation stays within the Basin boundary. And for that reason, delta X naught, perturbation across the boundary, does not appear in the equation for the Y variables. And otherwise, for the X variables, we need to use this recursive formula, the Van of linear equation for the growth of perturbations. And main observation is that well, first we plug the dyn in here, matching the indices, and then we divide over by dy naught. And that's to get the slope on the boundary. When we divide by powers of this Lyapunov number, we divide dxn, then it vanishes because dxn is a bounded quantity, because the perturbation is a special one, such that you stay in the boundary. And so you end up with this expression for the slope. And if the Lyapunov numbers are time independent, then you just have, instead of the products, these powers of lambdas. And you realize that what you have here is a power series of the ratio of these Lyapunov numbers. So clearly, you have a non-divergent series only if lambda y is smaller than lambda x. So you have a rough fractal, a divergence series when it's the other way around. So you have a more unstable in-boundary dynamics than cross-boundary. And we can add the comments that the condition will not change if these lambdas are time-dependent, actually, because we need to keep in check this index of small j. So basically, you still have the ratio of the 5 minutes, thank you, the ratio of lambdas, but in the sense of a geometrical average, and then that would be an arithmetic average for the f1 of exponents. And same story with nonlinear coupling instead of just an additant one, which leads to this time-dependent epsilon I. So still won't change the condition. And then you can bring it even further, considering the high-dimensional case, where what you get is just a directional derivative. And instead of a single power series, you have a number of power series, which is basically the dimension of the phase space minus 1, because you have one variable, which is the cross-boundary variable, and all the rest are in-boundary. So each of these series, each of these capital D minus 1 series are convergent if the cross-boundary dynamics is less unstable. We can also observe, make the observation that although this roughness is a global property because it's decided by the average diaphragm exponents, it's also a local property because the slope, as we examined here, is defined locally. So that means that if we had a Basin boundary, which is a filamentary fractal, so readily a fractal, then upon perturbation, we can just roughen it up the same way as a simple Basin boundary, because you are enough to look at one filament. The filamentary factor would be infinite layering of such filaments, but for the condition alone, you can only look at one. We can derive some dimension formulae. There are some interesting stuff here. It turns out that the dimension across the boundary is 1, which is the other way around for filamentary fractals, and the non-trivial fractal dimension is across is in the Basin boundary, and it's determined also not only by the F1 exponents, the ratio of them, that gives the condition already, but the pre-existing fractal dimension. And we can, of course, check our formulae, the dimension formulae, in a minimal model for a rough Basin boundary. Very interestingly, it's just a linear model for the unstable cross-boundary dynamics, and we need a chaotic one for the in-boundary dynamics, and we pick the parameters such that we satisfy the condition, and indeed we can find a complex Basin boundary when we initiate a large ensemble and see which way they end up, go that way or that way. I skip these through. We can also have a minimal model for this new or more complex type of fractal, where filamented and rough properties are mixed. So for this, we replace the linear model for the cross-boundary dynamics by a nonlinear one, for which you have readily a filamentary structure. So along this line, you have a Cantor set of filaments as an invariant object. And on the other hand, we still need a chaotic dynamics. I couldn't use the 10 map again because then I wouldn't find a good parameter combination for this mixed fractal property. So I used a chaotic map which doesn't have a single 10 but four 10s. It just makes the system more chaotic. And then we can derive formulae for the two Lyapunov exponents, the escape rate and the non-trivial dimension. And actually, with the use of these analytic formula, could I find a good parameter to actually demonstrate the existence of this structure. And indeed, we did obtain such a fractal. It's self-similar. You can't easily see, but here are little boxes where I zoomed in on this fractal. So there are subsequent zooms. And the calculation of the fractal dimension is successful, but not in terms of capacity dimensions, but we found that when we look at the information, the scaling of the information with respect to the box size, we have a much better scaling quality. And the number for the fractal dimension as measured is 0.84, while it was predicted to be 86. So we have confidence that with our technique, just traversing the Basin boundary by a line and measuring the uncertainty exponent or the Q dimension of this line, it's not this trivial d equals 1 dimension that we measure, but a non-trivial one that we could predict. And in the case of the mixed fractal, even if this contribution by roughening is very small, the precision of measuring the dimension is good enough that we can ensure that the formula is confirmed. And yeah, so it's just a final remark that we could demonstrate that what we measure by such a simple way is not a trivial fractal dimension, but the non-trivial one, the Q dimension of the Basin boundary. But that also means that just by measuring dimensions, we cannot actually know what sort of fractal we are dealing with. But that also means that it doesn't matter, at least from the point of view of the predictability of the second kind regarding the outcome of the system. But if someone is curious and still wants to know is a filamentary or a rough fractal, then you just have to apply theory and measure the Lyapunov exponents and check which one is smaller or larger. And that's something that worked in this case. And I stop there. Thank you very much.
Okay, thank you for a very nice talk, which lasted just a little bit too long. But as Socrates said, you cannot learn without asking. So, we'll take a few minutes for questions. Yes?
Well, I have a comment or a question on that. I mean, about the prefactor when you have systems for which the saddle is not a point, but it's rather.
Please speak up.
Thank you. So it is something that is not understood how to compute the prefactor when you have a saddle point which is a roof or which is chaotic. I think the formula of Meyer-Einstein and the one we derived ourselves are valid only for point attractors. And actually, even when it is a periodic attractor, the saddle point, then the formula is not correct. I mean, you cannot use. So it's a very interesting research subject,
Thank you very much. Actually, I was wondering about that. I knew that your equation was only valid for a saddle point. I didn't know about the invalidity of chaotic or even a periodic saddle. Thank you for that comment.
I understand that the prefactor is a little industry which is represented here by a number of people who were cited by Thomas. Okay. Well, if not, then thank you very much.